Now we're going to take a look and see how we can change the momentum for an object. This is something we call impulse. Impulse is the change in momentum. Although we use a different symbol for impulse, it's really delta P in these cases. And we have to remember when we say impulse, again, we're just saying how much are we changing the momentum of an object through some type of applied force. Now, impulse is a very important concept in collisions because, again, we said in collisions, our momentum is going to be conserved. So looking at this idea of impulse, again, anytime we're looking at the change of some type of quantity, we're looking at how the final quantity compares to the initial quantity. So in many cases, our impulse, our change in momentum, is going to be what is our momentum after an interaction has taken place. More specifically, it's usually a collision compared to what was it initially. Now, if the mass is constant, which it almost always is in most of these cases, we'll see the case at the end of the chapter where we have rockets where the mass is changing very rapidly. We can just say that our impulse, our change in momentum, is the mass times the change in the velocity. So let's take a look at an example of an interaction. Here we have a fastball from a pitcher coming in at about 42 meters, 42.5 meters per second. It's hit by the batter. It leaves at 48.2 meters per second. What is our change in momentum? Well, here the vector nature of momentum is very, very important because we see that the speed hasn't changed all that much. We went from 95 miles per hour to 108 miles per hour, or 42.5 meters per second to 48.2 meters per second. That's not a large change in speed. So we'd think, well, there wasn't very much momentum change here. What's true here is because the change in speed wasn't very large, the change in kinetic energy might not have been very large. However, the change in momentum was very significant here because if we look, here's our vector for our velocity for the incoming ball. Here's the vector for the outgoing ball. So direction's very important here. It's not that we've changed the speed by a marginal amount. We've changed the velocity significantly because not only have we changed our magnitude, but we've also changed the direction. So when we do this, we have to assign a negative sign for the incoming direction and a positive sign for the outgoing direction. We could do that differently, but the way that this picture is set up, the positive x direction would indicate outgoing. So here I look at the final momentum, 6.99 kilograms meters per second, compared to the initial momentum, negative 6.16. If I take the difference between these two, I see that the difference is 13.2 kilograms meters per second. So the impulse here, the change in momentum is very large, even though the change in kinetic energy might not be all that significant. Now, we can write the change in momentum, okay, the infinitesimal change in momentum, dp, okay. The textbook that we use uses J. Unfortunately, J is used for a lot of other different quantities, but we're going to use J here. We say that the infinitesimal change in momentum here is equal to the force applied. Obviously, the more force we put on something, the more it's going to change the momentum, times the infinitesimal time that's gone by. So for our total impulse over the entire time of the interaction, we can rewrite this as an integral where T1 represents the beginning of the interaction, T2 represents the end of the interaction. Oftentimes, these are very, very small. And this is equal to the integral of force integrated as a function of time. So that is a change in momentum. And what this tells us is two things. One, the change in the change in momentum, the impulse, is really dependent on the force that's being applied. The more force you put on something, the more you're going to change its motion. So it's completely obvious here that a large force is going to affect a change in momentum much more quickly. Also, what is apparent here is that the longer we put a force on something, the more the momentum is going to change. So if I'm in my car and I'm pressing down on the accelerator for a longer period of time, I'm going to affect a larger change, an impulse of my car. I'm going to go faster at the end, the longer that I accelerate. Likewise, if I press the brake pedal, the longer I hold my foot on the brake, the longer I'm going to decrease my speed. Eventually, I'll come to rest if I press on it long enough, hopefully, and the larger the impulse is going to be. So again, we can see this, that for a constant force, our impulse is just going to be the force times the change in time. However, if it is a non-constant force, then we have to integrate. And we saw this again when we did work. Work was the integral of force over distance. Here, we're taking a look at the force over time. All right, let's rewrite this. We can again see that the impulse is equal to force times the change in time if the force is constant. If not, this force becomes the average force that's acting, okay? And again, we already written our infinitesimal impulse as being the force times the infinitesimal time. So I can actually take this equation here. I can divide both sides by dt. Let's ignore this center right here. Divide both sides by dt. And I get a very interesting result. I get that the force is equal to dp dt. Okay. Now, we've seen a similar equation before, and we saw this in the form of Newton's second law. We saw that the net force acting on an object was equal to the mass times acceleration. Or we could also write that as the mass times the change in velocity divided by the change in time, if again, the force was constant. Now, we said F equals ma is Newton's second law. Of course, this is not always true, or we can't always use this form, because the mass may actually be changing as a function of time. We see this with the rocket. So this is actually a truer form of Newton's second law, where the net force is equal to 2 dp dt, and F equals ma actually becomes a special case. Okay, so here's the way we first present Newton's second law, with acceleration as dv dt. Here's the way that we can take that special case where the mass is constant and rewrite it as a more general case for Newton's second law, where the net force is dp dt. And again, this is a more general form, so this can also be used not only for objects that have a constant mass, but also for objects where the mass is changing, such as the cases for rockets. Okay? All right, so let's take a look at this graphically, because again, it's oftentimes better to visualize what's happening here. And if we take a unrealistic case where the force suddenly goes on an object and force suddenly goes off an object, we would get something like this square pulse right here. And we can say up to about 3 seconds, there's no force acting on the object, so the object, whatever its momentum is at the beginning, will be its momentum at the end. But suddenly we turn on a force instantaneously, and we're applying 100 newtons of force to it until we get to about 7 seconds, so 3 to 7 seconds. So for about 5 seconds, we apply this force, and then we ask ourselves, well, what is the impulse here? Well, that's not hard to calculate here, because we're taking the integral, and the integral of a constant right here, we can just put the constant in front of the integral. You can put the 100 in front of this and just integrate time here. Again, 7 minus 3 is an easy one. I said 5, didn't I? It's 4. It's 4. So 4 times 100 gives me an impulse of 400 Newton seconds. Okay? So that is one way that we can calculate the impulse. Again, we can actually do the integral Or we can look at a graph and say, well, how much area do I have underneath this curve right here? This area, of course, represents the impulse acting on the object where the force is interacting. Most interactions, especially for collisions, do not look like that. They look more like this Gaussian curve. And again, it really depends on the type of interaction that's taking place. It's almost impossible to create a force which goes from 0 to some discontinuous value. It's more likely that when two objects come in contact first, the force is initially 0. And then as a first touch, they start pushing on one another. They compress, reach some maximum value, some maximum force. And then as they rebound off one another, that value begins to decrease more and more. So again, we can look at our equation for our impulse, our change in momentum, is equal to the integral of force as a function of time. And if we can integrate that function, we can come up with a value for the change in momentum. Now, we also say that, yes, we've got a time varying force right here, but if we take the average force over time and multiply it by my change in time, again, first contact was made about 3 seconds, then final contact was lost about at 7 seconds. If I know the average force right here, you might recognize for a Gaussian, what is that? The half maximum at full width. I'm saying that backwards, full width at half maximum. But in any case, if I know the average force and the time, that is also equal to the impulse here. All right, let's look at different types of interactions here. Let's say we have a hard collision, a very rapid interaction that takes place between two surfaces. If that happens, we know that the time of the interaction is going to be very, very small. Now, in the case of a baseball hitting a bat, that's going to happen in times that are much smaller than what this graph shows. But what we see here is that when the interaction takes place, the change in momentum is going to be equal to the area underneath this graph. So if we effect a change very, very quickly, this is going to produce a very sharp peak with a large maximum force. Now, think about this. In the case of collisions, if we're trying to take a look at safety, it is the force that we're most worried about, because if the force exceeds the braking strength of, unfortunately, let's say our bones, if we're hit with something where we have an interaction where the force exceeds what our body can take, we are going to receive an injury. So hard collisions, very rapid interactions, are something that we try to avoid in sports situations, in automobiles, in any type of thing where we want to avoid injury. If we can extend the interaction time, I can flatten this curve right here. I can spread the area over a larger time period, and that will affect a less severe interaction. So you can see right here, if my interaction takes place in 2 seconds, again, this is a longer interaction, so calling this a hard collision is probably not appropriate here. But in 2 seconds, if I could stretch that out instead to 10 seconds, I would go from a maximum force of 100 newtons, spreading it out to 5 times the time, to a force that is, this should be 20 newtons, 100 newtons to 20 newtons. So I apologize for that graph. By extending the interaction time, we can reduce the forces of a collision. That's going to be important in a little bit of a moment. Let's go back to just talking about impulses. Here we have a serve, which is being made from a speed of 0 to 55 meters per second. We want to know if the interaction time is 4 milliseconds. What would the impulse be here? What's the average force? So again, We're going from 0 momentum to a momentum of 3.3 kilograms meters per second, or 3.3 Newton seconds. I know that this is my initial, this is my final momentum. My impulse, this should be J, is equal to the change in momentum, which is the average force times time. The average force here, our change in momentum, 3.3 minus 0, divided by the time, 4 milliseconds, is 825 newtons. Okay? Here's another interesting way of using momentum to find out a force. If you've ever seen firefighters with a hose, and the fire hose is giving off a tremendous amount of water, you know that there's a lot of force behind this, and multiple firefighters usually have to get on the hose to prevent the reaction from the action of the water coming out. Here we have a small garden hose, and we want to know, okay, so what is the total force from this hose? If we have 1.5 kilograms per second coming out of it and shooting out about 20 meters per second, that's pretty fast, 40 miles per hour, 45 miles per hour. We can use this, this equation right here to find out what my force is. So again, here we have mass per unit time. I'm going to convert that to mass times velocity divided by unit time, or momentum per time. I know that momentum per time is equal to the net force. So here we have a change in momentum per time of 30 kilograms meters per second. That's basically my force here. So again, what I did is I took a mass per unit time, I multiplied it by velocity, and that gave me my force or momentum divided by time. Basically Newton's second law, but arriving at Newton's second law a different way. Mass divided by delta T, multiplying it by delta V. Once again, momentum, usually momentum, we want to break into its orthogonal components. Later on, this will be very, very important when we talk about conservation of momentum, where each orthogonal component has to be conserved before and after an interaction. Another important equation relates kinetic energy to momentum. Because kinetic energy is 1/2 mv squared, okay, we can substitute V. We know that momentum is V divided by M. So P squared is going to be V squared over M squared. I'm sorry. Yeah, V squared is going to be P squared over M squared. When I combine it with the mass here, the mass in the denominator goes, one of the masses in the denominator goes away. So again, very important equation here relating kinetic energy to momentum. And we can see that kinetic energy increases faster than momentum. We've graphed kinetic energy as a function of momentum here. And if we flip this equation around and solve for momentum, momentum is equal to the square root of twice the mass times the kinetic energy. Okay, let's apply this to a real-world situation. Automobiles, although they're getting more and more expensive to fix, are becoming far safer than they were in the past. And one of the ways that we've made them safer is to design them to actually fail, to design them to actually crumple up in a collision. Seatbelts have also helped us reduce the injuries by preventing the body from impacting with the dashboard or the steering wheel. This allows the body to come to rest at a much more controlled way. And of course, airbags also allow us to do this. All the designs of the car to increase safety during a collision are really here to increase the time of the interaction, to stretch out the interaction, because this will reduce the maximum force that the body is going to feel. So again, we can see that if a car were designed so just the bumper would crumple up in an interaction, let's say it would just give 20 centimeters, that would be far too rigid in a high-speed collision to expect somebody to survive. Here is a car traveling at 27 meters per second, and let's say that it makes a collision with an object, and that collision takes place such the object's solid. maybe a concrete barrier. That's going to be very, very troubling because uh, if the time that it takes the car to come to rest is like 15 milliseconds, then what we have happen here is we get a very, very high acceleration of 180 Gs, and that's almost certainly not survivable. So how do we extend the time of collision? Well, what we do is we create a car which will actually crumple up and reduce the maximum number of Gs that somebody might experience in the case of hitting a solid barrier to something more survivable. And again, if you look at the way cars are designed, they are designed to actually fold up in an interaction. Here we have a test being performed to see how much this car will crumple up. Usually the engine will drop to go below where the passenger is. The passenger will be allowed to move forward in their seatbelt. And essentially every part of this car is designed to extend that time of the interaction. And that really goes a long way to increase the survivability in these crashes. So what was, perhaps a not survivable impact now becomes survivable if we make that distance that we allow this interaction to take place increase by fivefold. We know that the acceleration is going to decrease by a factor of 5, and that becomes more survivable. So again, seatbelts restrain people, takes more time for them to stop. Airbags also increase the time that the body is brought to rest. And this is an important point with airbags. Airbags, if employed properly, can help the safety during a collision. Again, it's a very simple device. The crash sensor detects a negative acceleration or acceleration of more than 2 Gs. The reason why we use 2 Gs is approximately 2 Gs. I'm not sure about the exact particulars here. They might set it to be a little bit more, is because you can't accelerate at 2 Gs with these cars unless you put a rocket on it, and you can't brake more than 2 Gs. Coefficient of friction is just not large enough to allow the motor or the brakes to affect such a large acceleration. So the crash sensor detects an acceleration which is greater than what the car can perform, and it understands that a dangerous interaction has taken place. So this triggers a fast chemical reaction, not an explosive chemical reaction, but a very rapid chemical reaction that happens in milliseconds to inflate the airbag. They originally tried this with compressed gas, but compressed gas can't fill the airbag fast enough. So they now use a rapid chemical reaction. So again, here are some of the actual sensors that are used on a car that send a signal to a computer. The microprocessor will then take this igniter, which starts a reaction of sodium azide mixed with potassium nitrate. And this is an exothermic reaction, so heat is released, but it releases a lot of nitrogen very, very quickly. And again, it's very fast, but it's not so fast that it produces a shock front, which would be very, very dangerous. So the airbag fills up faster than the body can come forward. But it's important to understand that this airbag is coming at you at 200 miles per hour. So if you're too close to the steering wheel, it will deploy at 200 miles per hour and then come to rest to zero. So the first 2 to 3 inches of airbag deployment are very dangerous for a person to be. You should never be that close to where an airbag deploys. You should never have your feet up on the dashboard. You should never have your seat so close that the airbag where it's deployed is less than about 10 inches, because you want that airbag to come to rest by the time your body comes forward and meets with that. Now, in NASCAR, there were a number of drivers who were killed by a type of injury that would fracture the very top vertebrae due to a high-speed impact, usually with a retaining wall. And suddenly this became a crisis, and they were trying to figure out how do we fix this problem that's killed some famous drivers. I don't know much about NASCAR. Adam Petty, Kenny Irwin, Tony Roper, and Dale Earnhardt Sr., however, were names that I recognize. And what would happen is the head would snap forward due to its own inertia on impact. And this would, create a fracture because of the vertebrae and kill the driver instantly, because the head's inertia would bring it forward where the body was being restrained by this 5-point harness. So what engineers figured out is, well, first of all, we want to be able to get the driver out quickly if there's a fire or there's some other dangerous situation. So to strap the helmet to the seat would be not something that drivers would want. So they built instead is this support system made out of carbon fiber, which would sit on the driver, be part of the driver's body moving forward. And what we would do is strap the helmet to this, use something called a hands device. It'd just be a little tether, and that would cause the head to move with the body, and this would prevent the head from rotating too far forward, where this type of injury would take place. So again, this shows that we bring the body to rest in a controlled fashion. By strapping a body in, there can be unintended consequences where loose parts of the body can move. And one of the most common injuries in a car crash is fracturing feet and fracturing legs, because the legs are free to move forward during the impact. You can also fracture your arms. Safety equipment also works on this principle of trying to extend the time of the interaction, make the time of the interaction longer and longer. Here is football equipment. You can see it has a hard outer shell that distributes the force of impact for a larger part of the body. And then there's soft cushioning material inside. That's also true of helmets. And what happens here is the cushioning takes time to compress. It extends the time of the interaction, so it brings down that maximum force that we talked about before. So again, sports safety, regular safety helmets are there to prevent the head from experience a very rapid acceleration, a very large amount of force, which would can produce a fracture of the skull, which can be very dangerous, or it can also produce an impact of the skull, a concussion with the brain, and that can also obviously be very, very serious. So again, the whole idea of padding, increase the time of the interaction, and where we have vulnerable parts of the body, maybe the chest, maybe the shoulders, which is a floating joint, create this hard surface that can spread the force over a larger area.